Hi, everybody. Welcome back after lunch. My name is Quincey Koziol. I am a principal data architect at NERSC, at Lawrence Berkeley National Laboratory. And I will be giving you guys a moderate level, not really high level, not really low level detailed view of HDF5 and how to work with it and debug problems and look at performance issues and everything. So building on what Phil and Rob have been saying today too, so there's occasional points where I'll say, and just use Darshan for that, right? Okay. But there's specifics about HDF5 that are really valuable, and occasionally contrasting with PNetCDF and parallel NetCDF, we'll have a good conversation about those things. I'd like to really encourage people to speak up and ask questions. I am super happy to answer anything you've got along the way. I'll try to pause and encourage people to ask anything that's on their mind. There's occasional confusing points in here, and I'd really like to make certain that they're clear and clear enough in my slides. And go ahead and get started. So one thing I will point out here is that at the bottom of all these slides, there's a URL, which ought to be moderately easy to remember and look up. And I've posted all the slides in the example programs in that Dropbox directory if that's easier to get to than the ones for the @pesc repository, which also has them. So it'll be there for the rest of the presentation. You can look at it whenever you'd like. So HDF5. Why would you do HDF5? How do I deal with these big problems that were coming along? How am I going to try to deal with file per process at the exascale zone, like million ranks, right? It's just not going to be scalable, right? Do you need to know all the miscellaneous muster and MPI things, right? How do we turn all the knobs and get everything to line up? Does that really going to impact and be good for your science production? We're trying to say the answers are like, no, right? Where do your checkpoint files go? All these kind of questions. HDF5 is here. It's what I would consider a middle level, perhaps high level, depends. It's not very domain science specific, but it hides that I/O complexity so you can concentrate on your science to the extent we have possible, right? It does tend to be a little optimized for a single shared file, but there's options and ways to work around those kinds of things for multi-file HDF5 storage as well. So I'll start off with the big overview about HDF5 and talk about the data model and what that looks like so you get the terminology and you understand the concepts going in, then go more and more into detail about how do we write an HDF5 program, what does it look like in a parallel scalable scenario, okay? Some of my examples are in small numbers of processes so you can run them on your laptop, but we've scaled out to tens and hundreds of thousands of processes at various DOE, NSF facilities around the world. So, HDF5. In case you're wondering about the acronym, Hierarchical Data Format version 5. Versions 1 through 4 are completely incompatible. If you run across something that's called HDF4 or really archaic 3.2.1, it is not this. It requires a different piece of software. The APIs are completely different. The file format is completely different. It's a different thing. We built off the ideas that we learned at the time, but it is a completely different package. It's not scalable. It doesn't do parallel I/O. It's not what we're talking about today. But HDF5 is designed kind of thinking about it from the bottom up. We have an open, well-specified file format, which I would encourage you not to go learn. You don't need to know the details of the bits, okay? Just people have done it. People have replicated the HDF5 reading and writing to the file format outside in a black box scenario outside of the HDF5 library. So we know it can be done, but just really not your problem. We distribute a lot of open source software built directly to work with the files that you produce. And then there's an enormous ecosystem built around HDF5. Lots and lots of software packages all around the world deal with HDF5 and help you with data analysis and visualization and importing and exporting and all the other data processing issues you might run into. And at the very highest level, kind of classes and the data model, how do you think about your data, okay? So that's where we're gonna start, at least conceptually. So HDF5, well, it's an interesting thing. What is it? Well, it's kind of like XML in a sense. It's designed to be portable, The files are self-describing. They contain all the information they need to query them and understand what's going on. It has a lot of capabilities for rich metadata, and it's extensible. Given the bias we have towards HPC and high performance, we want to have a binary representation. It's not text, right? You cannot VI your HDF5 file. It's compact, it's scalable. It's a lot, in some senses, like PDF. Sometimes we've talked about it as the PDF for science, right? It's portable. We've gone from feature phones. I had people at Nokia email me in the early 2000s, like, hey, I got this funny idea. All right. All the way on up to today's big supercomputers, and we were just joking the other day that we used to support VMS and all kinds of things that you don't have to deal with anymore. HDF5 also has this nice hierarchical notion, so it's kind of like having directories and files inside of another file. So it's a graph, when it gets right down to it, a graph representation inside of a file. And it has some commonality with databases that you do random access and subsetting and things like that. It's not really any of those things, though. It's kind of designed to be a specialty thing that was principally organized for science. It gets used in business and engineering and other places as well. But it combines ideas from all those places. So there's aspects that we draw on from all those different fields of data storage and data management. HDF5 is designed to be used in high volume, complex scenarios. And like I said, it's every size and shape of machine out there. You can port it around wherever you'd like. We try very, very hard to make certain that's easy. It's obviously designed for flexible and efficient I/O. Enables your applications to evolve. You can extend your HDF5 usage over time. So today, I'm only storing a single data set. I put a couple of attributes on it. But the next iteration of my software, I need to store 3 data sets in another group and put some hierarchy in here and have a more complicated set of attributes that I add done. Perfectly easy to do. And ideally, we want your data back in 50 and 100 years, right? One of the major clients for using HDF5 is NASA, and they do a lot of their Earth-observing satellites to gather climate modeling information. And it's not very useful if the file format has to get exchanged and updated and goes out of date in 5 years. So we can access data that we produced 20 years ago, and we expect people to be able to access their data indefinitely, ideally for as long as we have support and good quality maintenance on the library. There's a tremendous, like I said earlier, ecosystem built around HDF5. Many, many commercial packages, open source packages, government agencies, industry that uses HDF5. There's a very, very broad set of applications and teams out there who use it and draw on all the information we have. So I'll talk about the data model here and kind of start building up the programming stuff, but anything on the kind of general background ideas? One thing I'll add in here is that the principal maintainer for HDF5 now is a small nonprofit in Champaign, Illinois, called the HDF Group, and they do the ongoing support and maintenance, try to collect everybody and keep them all moving in one direction. So there is an official nonprofit organization that is tasked with this. It's not just kind of a general open source package. Yes, ma'am?
What goes into the long-term data preservation aspect?
Well, several pieces of it. We do long-term maintenance on the data files themselves. So we test to see if we can read our old data files still, right? So very old, 10, 20-year-old data files, we make certain that we can continue to access those. And then every time we upgrade the software, we regression test back to make certain that we can update those things.
But I thought, is that not partially a hardware thing about like what you're storing on? I'm totally.
Well, these are just generic files in a sense, right? So you can port those, from today's hard drives and SSDs to tomorrow's flash to next year's holograms and whatever. It should just generally be a file that you could move along as time progresses, I'd say. It's not tied to a hardware architecture in any way, really.
I think the answer is HDF5 is independent of the hardware
right.
that it's running on.
Yeah.
Okay, but you don't have to move it physically ever, just
Well,
to.
if you want
for
to
the-
archive it, yeah, you need to move it somewhere.
Yeah, that's kind of on you, right? So wherever you put the file, you can access it with the software that we're providing.
Okay, so it's more of like a maintenance thing in terms of like people know what to do with it
Yes.
at all times.
Yeah, right,
Okay.
exactly. Good question, thank you. So progressing to the top level of the programming side of things, start talking about the data model. So HDF5 has 3 principal objects, classes in a sense, from an object-oriented sense of things. Data sets and groups and attributes, and I'll talk about all of them. And those use some of these other concepts, links and data types and data spaces. And they all get grouped together into a file, or sometimes I'll talk about it as a container because sometimes we're moving towards a post-file kind of era where we're dealing with object stores and other things that are not necessarily obviously files to a user. They might be a collection of files or behind some barrier that you don't know what's going on in there, but it acts like a file to you. So all those things are part of the data model. And realistically speaking, there's a couple more runtime objects that I don't talk about here, but it's not a complicated set of classes to say, oh, there's about 8 concepts that are important in HDF5, 3 really big ones. There's a lot of API routines, but if you kind of work your way in from the idea of these 3 basic objects, you'll have a good concept of what's going on. So files in HDF5 are, as I said, a container. They hold the data objects. And in particular, the principal one you'll deal with is HDF5 data sets. You can think about those things as basically a multi-dimensional array that holds identically typed homogeneous data elements. So every data element has the same type. They're all int32s, or they're all floats, some kind like that, right? Every array element is like that. In addition to just this blob of array, we have to store a description, some metadata that describes inside the file, so the user isn't trying to write this down in some separate file, but inside the file, pieces of metadata about the objects that we store. So in this case, I'm saying, well, hey, the data type, which is what the description of the elements are, is a 32-bit middle Endian, and the data space in HDF5 terms is the arrayness, right? How many dimensions does this array have, and how big are they? What are their dimension sizes? So in this case, it's a 3-dimensional 7x4x5 array, and the elements, I'm telling you, you can't tell from this, 32-bit middle Endian integers. Taking that apart, right? Well, okay, what's this data space idea? They described, like I said, the logical layout of the elements in that data set. And all the HDF5 data sets are fundamentally arrays. There's a couple of kind of degenerate forms of that. You can have data spaces that are null, right? It's the empty set. Like, I just put this data set here as a placeholder, or maybe I wanted to store an attribute that has a name but no actual value. You can do null data spaces, and you can have scalars, points, just a value somehow. You don't need an arrayness to it. Most of the time, you have what we would call a simple data space. It's a rectangular array, right? What's the rank? It's 2-dimensional, 3-dimensional, or 4-dimensional. We support up to 32. If you have some reason for more than 32, come talk to me. I will try to convince you otherwise. And maybe we'll have a conversation about why you need more than 32, which would be interesting. 5 is about the most legitimate number that people have come up with for me. It gets beyond 5, there starts to be some questionable logic involved, but it's interesting. So the dimension sizes, how big is it in each dimension? We support up to 64-bit values in dimension sizes, so you can have exabyte-sized arrays if you really could find a storage system that'll hold that for you. And you can extend it. So you can say, well, right now it's 100 by 100, but I want to allow it to get as big as it needs in this dimension and 200 in the other dimension, right? So the maximum dimension sizes in HDF5 can be larger than the current dimension sizes. Data spaces have kind of 2 roles in a sense. What I was just talking about, which describes the arrayness, and that's permanent, part of the object definition when you store it in the file. And there's also places where we use the data space and what we call a selection for subsets within those arrays, both in memory and in the file. And so you'll see this partial I/O, selected I/O, all kinds of different terms. We'll talk about it in much greater detail as we go on here. But that gets used, the data space is part of that model for getting your data out to disk. And that's transient. You just do that for the one I/O, you make a selection, then you don't have to use it anymore. It's not permanently stored. The selection is, the data is, the selection is not. So data types, so what are the elements made out of? We support a very broad range of things, probably everything that you can think of you might need. Integer, float, enums, you can do named things, red equals 2 kind of things, right? And then a wide variety past that. Most people will stick with your integers and floats. A strong subset deals with compounds or like structs or records like you might think of in database terms. If for some reason you're storing a vector of coordinates or some Hermitian matrix or something from your physics, occasionally it's nice to think about the array elements as an array themselves. And if you're trying to store a string or something else like that, you're dealing with what we would call a variable length sequence, either of characters as a string or a vector of integers or floats or whatever else you'd like. NASA does deal with these funny user-defined 12-bit integers off the satellites occasionally, so they were kind of a necessary part to support. And all of these things can be combined, right? So you can have an array data type for your elements. Each base type of that array type is a variable length sequence of compound types where the fields are, and you can keep going, right? We support the full nesting, whatever complexity level you'd like to go confuse yourself with later. Try not to do that. So this is a simple overview of a very straightforward data set, right? It's two-dimensional, it's 3 by 5. The data type is 32-bit integers. It stores obvious integer values as array elements. In C, you would declare this array type as 5 by 3, right? The fastest changing dimension in C is always the last one, and that's how we index it in HDF5 as well, but Fortran historically goes the other way, right? As long as you declare them and you tell HDF5 that, everything will be fine. Your data will be portable between C and Fortran, and it'll all work out. There's a more complicated 3 by 5 data set where there's a compound type with 4 fields, int 16, a character, int 32, and an array data type where the base type for that array is a float 32. So a little bit of nesting there to kind of show that concept. Anything, questions about this part of the, here's a data set model. I'll show you how they get stored in a second, but kind of at the high level, conceptually, this is like, oh, they're arrays. Okay, I know what arrays are. Okay, let me know if you have anything. So generally speaking in the file, so the buffer's in memory on this side, the buffer's in the file or on that side, the default is, hey, just shove this array in the disk, right? It's what we call contiguous storage. They're all kind of physically like you would expect in memory. They just get written out in one I/O operation directly to disk. If for some reason you want to do subset access and you'd like it to be in a nice pattern that you do on each rank in your MPI job or for whatever subsetting algorithm you're dealing with in your data analysis, you can chunk the data set and break it up into tiles, what we call chunks. And this is the mechanism for having extendable data sets if you want to have a dimension that grows over time, or if you want to compress those chunks. The data in your data set, it has to be stored in chunked format in order that we can index into the right locations correctly. So that's what the bottom level is showing here is, if your data is smaller, it's going to go faster to I/O, we hope. You're paying some compute to get it there into the compressed form, but then hopefully the I/O goes faster. And then there's 3 other forms that HDF5 can store your array data in, and they're a little less likely, but they're very useful in certain specialty circumstances. If you have a very small data set, like you're only storing 2x3 array as your data set, for some reason this is important to you, you can store it in compact form where it gets stored directly in the data set's object header in the file. So you reduce the number of I/O operations, and it brings in the data set's object header with its metadata, and it pulls the array data in one I/O operation. If for some reason you have data in another file, maybe it's another file format, something like that, you can describe where that is in the other file with an external storage for the data set and point at it and say, you know, hey, my data set is in HDF5, but really the data is over there in this other file. So this is really useful in certain circumstances for like bridging into legacy file formats or some portability problem that you've got with a piece of software that doesn't understand HDF5, but maybe it understands this other package. You can kind of make it work for both HDF5 and the other one. Yes, sir?
Can you merge different files together?
Well, you can do that. But the description in the object header can incorporate multiple files as places in the data set. So you could have any number of files over here that we referred to from within the HDF5 data set and say, hey, you know, offset 72 to 1006 were these elements in the data set, and, you know, file number 2, offset 3000 to blah, blah, you know. So you can slice up your file set however you'd want and then describe it to HDF5, and we'll just do HDF5 I/O and reach into your other files. It'll look like one data set to all the HDF5 ecosystem. MATLAB won't know the difference, you know, kind of thing. And in the last couple of years, we added a support, which is similar, but at a kind of a little bit higher level of abstraction for what we called virtual data sets, where not just at the byte offset level, which is how I was talking about these external ones, but with a selection in this virtual data set, I want to refer to elements in another HDF5 file at this selection. So you can set up a scenario where, say you have a light source and cameras taking pictures, and you've got 6 cameras for a frame of your image, right? And so each camera is outputting its own HDF5 file, boom, 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 multiple frames from each camera. But conceptually, that's one picture, right? So you'd like to create an HDF5 file with a virtual data set that incorporated all 6 pieces from the other cameras and have the HDF5 ecosystem understand that as, hey, this is one frame in an image, and I'm going to sequence through these guys. So this is a little bit higher level of abstraction, but it's conceptually similar to the external storage too. Question? Yes, sir.
So these are all just essentially arrays. So like say I had a external library that stored binary data, this would not be really a way of...
Well, it depends what you mean by binary data, right?
So like non-array binary data.
Well, again, you know, we could go further down that rabbit hole, but yet generally speaking, HDF5 understands arrays. You can think of arrays as one-dimensional tables sometimes, so sometimes that fits. But if it's truly really blobby and not very well described, like it's an XML text file or something else like that, it doesn't fit very well in HDF5. It's just not quite a good structure for it. So maybe, but maybe not for binary blob stuff. Yes, sir?
The last one, the virtual type, does it have to point to another file, or can it point to another data set in the same file?
It can go either in the same file or in another file.
For example, if I have a 4D structure and I want to create like a 3D out of that 4D data set, is it possible with
Yes, you can take slices out of individual HDF5 data sets, and you can actually turn conversely, right? You could have a virtual data set that had an unlimited dimension, and it was mapped on top of other data sets that had unlimited dimensions, and as those source data sets expand, the virtual data set will appear to expand as well. So you can do arbitrary mappings, effectively, yeah.
So you say something more on the performance aspect, using the virtual and external, which the FBI calls it wrong. Any reason why I would want to use virtual instead of, let's say, a 9 or like multiple HDF5 loading?
Yes, performance will be poor, not poor, but less than if they're all stored in one contiguous data set in an HDF5 file. Definitely that's going to be the case. You would want to use those in scenarios where, well, backing up a step. HDF5 only allows one process, unless it's an MPI job, one serial process to be updating an HDF5 file at a time. So in those cases with the cameras, and each camera is trying to update one, if it was all going into a single shared file, it may be very difficult to coordinate access to that single shared file. So you let everybody create their own file, and you stitch it together with that virtual, and later on you can repack it into a single file if you'd like. It's only for kind of online monitoring that you might want that really live aspect of it. But yeah, you do get well, I got to go over in this file and get this piece over there instead, performance penalty when you do that.
The virtual case, does it check that those actual files get overwritten by someone else? It's one of the things that you make bad.
Yeah, well, that's part of what they're good for, right? Is that you can change the data in the source files, and it's visible in the virtual file, because the virtual file doesn't store any data. It just refers to those files. So it's live updates, if you like. Anybody else? Okay. All right, so the next piece of the data model, we've talked about data sets, then these are attributes. Attributes are metadata, user-generated metadata that decorate or are additions to an existing HDF5 object. So they're very similar to key values in a loose sense. They're not a key value store in the sense that sometimes you encounter those, but all the attributes, they have a unique name that's local to that object. So you can have one data set with an attribute called X and another data set with another attribute called X. They're completely separate. And there's a value for the attributes, right? Attributes are, the value for an attribute is analogous to a data set, and it's described by a data type in a data space the same way. So it's a little mini array. They are designed to be small. You should not be shoving a gigabyte into your attribute. That's probably a data set. They don't support partial I/O because we assume they're small, right? This is like a 2x3 matrix that you just had as some kind of input parameter into your simulation. You just want to store it there as an attribute on your data set that generated the big data. And you can't compress or extend them. We don't expect people to do fancy things with them. They're just kind of augmenting the existing scale data and data sets. You can add them to groups as well. So I've said data set a lot there, but you can add them. Any object in an HDF5 file can have arbitrary numbers of attributes. All the attributes have to have unique names on that object, and each object is kind of separate from the others. So that's great. I've got this pile of data sets, and they can have attributes. How do we structure this? All these data sets aren't, unless we're going back to like DOS 2.0 with everything in the root group, you want some level of hierarchy to hold all these kinds of data sets that you're creating. So HDF5 allows you to create groups, and each one of these groups has links to objects in the container of the file. Showed in here at the top, it's similar to a file system in that there is a root group inside the file, and that points to other things. It can point directly to a data set itself, and lots of times people will throw data sets in the root group that say, this is configuration info. And then nested subgroups to have checkpoints for different time steps, or some visualization analysis, or whatever else is going on. I show here that this data set, for example, which I was trying to show has a compound data type, latitude, longitude, and temperature. That's actually shared. There's a link to it from 2 different locations in the file. So you can have hard links to, from multiple groups to the same object. And HDF5's link capability also, you can point to objects in other files. It's called an external link. Same way we had external data sets or virtual data sets, you can refer to objects in other files directly from within a group. Yes. All right, so that's the data model side of things. Any other questions, especially about groups or maybe attributes?
So can you have permissions for different parts of the file?
No, because that would require you to encrypt it. Because you got the software, man. And you get the file. You own everything. There's nothing we can do to stop you from a permissions perspective, really. But if we did add we've kind of prototyped around the capability of we could prevent you if we encrypted the data and then you were required to provide a key at runtime or something.
Or part of the data?
Yeah, maybe, you know, the metadata, but not the raw data, or the other way around, depends. So answer is no, you can't have direct permissions, but we could play with encrypting stuff for that purpose. Yes.
Yeah, in the case, for example, of that table, the two groups are pointing to it. How do you do it? I mean, like, it belongs to one of the groups, and then you do a hard link from the other one, or?
You would, for this data set, to create hard links for multiple groups, you would create the data set with a path that referred to one or the other, and then there's a link create call in HDF5 where you would say, hey, by the way, go create a link called, I don't know, whatever, temperature table or something, from this group to that object in the file. So yeah, you do a kind of a creation with one path, and then you add in hard links as you'd like.
If it was a big data set, then performance-wise, it doesn't matter in which group you use.
Yeah, it's totally independent of how you got there. It's the same on the file, exactly. And actually, you know, we ref count things in the standard computer science kind of way. So you can create a link one way and add a link later and then break this guy, and it's fine because the ref count is still above 0. I'm lying to you a little, but if you really care, I'll tell you more later. You can do anonymous objects and funny things, but it's okay. Oh, sorry.
Does that link to the external file, is that required to be in HDF5 format, or is that just like a file path?
In this case, what I'm showing is one that's actually an object in an HDF5 file. There is a capability in HDF5's package to define user-defined links. I can do whatever magic you want as long as at the end of the day you give me a reference to an object inside HDF5. So you could reach across the web or do whatever you'd like if you wanted to go implement something like that. So there's a kind of an escape hatch for those kind of things.
Do you see that maybe for HPC, all the users, no matter what application you use, you should all use HDF5 format, like neuroscience, like astrophysics, everything. That way is like unified. Is this good, or?
There's advantages to it, sure. You know, then there's a nice bigger ecosystem. Like Rob was saying earlier about NetCDF, sometimes there's advantages to going up a level where it's kind of a little more specialized for your science domain and everybody understands NetCDF data, so this is the terms we deal with. Now, as Rob was saying, you know, NetCDF4, that release and further, have an option for storing HDF5 as their storage format, so you really are using HDF5 underneath NetCDF, even if you don't get too much into the details. And there's occasional places where, since we've limited resources and time, haven't had a chance to optimize for some use case. And so, yeah, there may be domains where currently there's no good way to go shoehorn that into HDF5. I could probably come up with something, but it would probably be ugly. So generally speaking, for most science data and many business and engineering and other kinds of scenarios, this works pretty well, as long as you don't need super specialty things. So, I mean, like we don't do locking like a database does. We don't do atomic access and those kind of things, right? So if that's your thing, then you got to use a database, right? If you think you're getting strings and text data and you're doing JSON stuff, it's not a great fit into an array, you know? So you could shove it in an HDF5 data set and call it an unlimited length character data set, and people do that, but it's not a great fit, so it depends. Most types of numeric data does pretty well, I'd say. So we'll go from the high level in the data model down into the software pieces of things. So I'm pointing you at the HDF Group's web page for HDF5. But realistically speaking, probably many of the systems, if not all of the systems you have today, have HDF5 pre-installed by default. optimized well for that version of architecture and, you know, whatever MPI and storage system they've got. So if you want to go look things up, this is fine, but probably it's already available and you don't have to build your own version of it. Kind of as general background, the library is written in C. There's some historical pain about that, but anyway. There are C++, Fortran, Java, Python, well, the version you get from this website, from the maintained version from the HDF group, has those language wrappers. But there's Python wrappers and Ada wrappers and Pascal. I know of a COBOL, C#, Ruby, Perl, I mean, everything else, right? I mean, so if you've got a favorite language, you can probably get to HDF5 data. And in addition, the package that you download, if you'd like to, has some common command line utilities. I'll talk about a couple of them. There's a few more, and they're all well described on the website there. If you do have a pre-built binary on your system, you can look at the libhdf5 settings file to see what the configuration was for it. Did it include compression method X, right? Or does it have a Fortran wrapper, this kind of things, right? Typically, the pre-built ones that you download have a couple of compression methods built into them or require them. The tools that you might use right off the bat, H5dump is really good. It's like somebody points you at this HDF5 file and you want to just get a quick glance of what's in here, right? Command line tool to kind of display the group structure. If you really wanted to look at what the array elements are, it'll do that. I wouldn't recommend it for gigabyte scale stuff, right? Lots of text output. If you're writing a pretty straightforward HDF5 application and you just want to get example code working, we have compiler wrappers similar to MPI-CC that include the header files and all the libraries you'll need. But many people are already pretty far down the path of, I'm already using MPI-CC and you're going to have to look up the header files that you grab. It's pretty straightforward. There's a Java browser if you prefer the GUI version of H5dump, and many examples in many languages if you'd like them. Questions about this stuff? Okay, so I'll start talking about code now. Okay. So, big picture view of, wow, the HDF5 library, right? So the HDF5 library is this chunk in the middle, right? All those language wrappers and other high-level APIs, applications that call C directly, and they're up above. They'll reach in and talk about data spaces and data types, groups and data sets, some properties that you want to tweak some behavior of an object or your access to the file in some way. There's a tremendous amount of internals going on here. It's about 300,000 lines of code in the library, really. And then we reach down and talk to eventual storage in some way. The default is with a POSIX IO just into a single file. You can talk to two files, which is convenient because sometimes it's very nice from an IO performance perspective to put all your metadata in one file and all your raw data elements in another file. So you can have that split access. Obviously, what we're here for today is to talk about MPI, and you can write your own. If you've got some storage backend or you want to reach across the web or stream data across a socket or something funny, you can custom write your own how to get to the HDF5 file, wherever it is. So the API that you're going to deal with, I'm going to talk about C because it's the most common lingua franca of what we deal with. It's fine to go into Fortran, C++, everything else, but right now we'll deal with C here. Like I say, there's lots of wrappers in other languages. And in C, we have no classes, right? It's so fun. So this little prefix here, the character that you stick in the front, this is our namespace, H5, right? D is for data sets, F is for files, S, D was taken already. Data space, okay? So everything has a letter in that three-letter prefix, right? That tells you what class of interface you're dealing with, and then everything else is a method name effectively, right? Dataset reads, file opens, dataset closes. There's a lot of API routines. If you thought MPI had a lot of API routines, we're in that ballpark, right? A couple hundred. it's pretty straightforward to get started. There's a lot of examples that show you with seven API routines how to write an array out of your, out of your code. So you can get in there, and everything else is kind of like refining and augmenting, and how do I like tweak in this particular way and get this particular benefit one way or the other. So that's what we're going to do here. It's very C, right? You open or create the object, you access it potentially many times, read and write, and then you close it. You have to remember to close things, right? So otherwise you just get, we do not garbage collect. Well, I'm lying a little again. But we do not garbage collect, and you need to close the stuff to release your resources. If you want some optional behavior out of what the defaults are, and we'll go into that here as well, we have properties in HDF5, same way that MPI has info objects that allow you to kind of tune the behavior of the underlying implementation. You'll tune objects or file behavior or IO behavior with properties. So very high level, very simple 7 functions to go create and store data in a data set in an HDF5 file. So create your file, create the data space, create a data set, read or write your array elements, close everything down. You notice here that I don't talk about a data type, right? There's some very easy basic data types like float32. There's nice definitions in HDF5 for really simple things like int32s, float64s. Those are all predefined and available to you because I can, right? But arrays, I have no idea what size your array is. And there's millions of combinations, right? So you have to describe your array in the file and in memory, but there's a lot of predefined data types for the most common sets of things. If you want a combination of a compound type with a lot of fields, you have to do that. Arrays, variable length sequences, those kinds of things are not predefined, but there's functions to build them up for you at runtime. So if you just have an array of floats, this will get you there. Any questions about that part? Just really early programming idea? Okay. One thing I will mention here too, kind of at this very straightforward, early, simple level is we fully describe the data types that you create. So we will say native int. And if you're working on a middle endian machine, which is what we mostly have today, you're going to be dealing with that going into your file as your native format. If you later on go off and read on a big endian machine, maybe one of the IBM boxes or something, it's going to do a type conversion to flip the endianness of your floats around, right? So depending on your IO access patterns, you may want to target your destination with a data type that you create in the file and let the type conversion happen in the best place. Is it on reads or on writes? So from a simple example, you can at least think about that. Hey, in memory, I've got native ints or floats, but in the file, I want big endian ints or big endian floats because later on, I'm going to read this array a million billion times on some other architecture, and you're going to pay the penalties someplace for that type conversion. You might want to pay at the place where it happens the least number of times. So other common routines to get started, right? This is kind of like, once you get past that first 7, this next 20 is a good start. How do you do subset IO? I'll talk about it here, but select hyperslabs, select elements in the data space. If you need to retrieve the data space for what is the data space, the array size of this data set on disk, that's that H5D get space. So for this data set, what's the data space? Right? Give me a data space object. Data types, similarly, there's a D get type in there. You can check. One thing that you'll see here, this type equal. We give you back IDs for everything in HDF5. You cannot compare one data type ID to another data type ID because you're just comparing integer values in memory. And that comparison won't tell you that this is a float32 and that's an int64. You have to use your T equal or one of those kind of routines that query those things to get those derivative values out. groups. There's a bunch of link API calls too that create hard links and other things. Attribute creation, properties. These are the basic ones to set chunking for your data set and then set deflate or compression for that. So gradually getting close to HPC. Any questions before we start talking about parallel stuff? Okay. Okay. So again, I've kind of probably been using some of these terms already, but data and metadata inside the files. When I talk about various metadata problems, up to now I might have said, oh, attributes are user metadata, but a lot of what I talk about for performance issues and other aspects of parallel I/O, the actual HDF5 infrastructure metadata is what I'm thinking of, the descriptions of your objects in the file, those kind of things. So just kind of, so data is the problem size data, or the data set elements sometimes. And like I say here, there's a bunch of metadata, HDF5 metadata, that gets stored in the file. It's necessary to be self-describing and to kind of give you your data back eventually. So, well, that's all great, but maybe why would I want to use this? And Rob covered this earlier when talking about MPI/IO and NetCDF, PNetCDF. Ideally, you want to be focusing on, your science and your application domain and not thinking about how am I going to tweak this because I'm porting my app from, Theta over to Cori or something else from one machine to the other. You want the I/O middleware to handle that for you. So if you deal with HDF5 at a high level, we give you a bunch of portability, both in terms of performance, and your data will move from one machine to the other and be perfectly accessible. Your code should port over, at least the HDF5 parts, very transparently as well. And again, principally, if you're trying to use a single or a few shared files, HDF5 is very good at that. It certainly devolves down into bad use case scenarios that we've talked about earlier for file per process, right? You get up into the hundreds and thousand ranks and you throw massive amounts of files at the file system, it's not going to be happy with you. You can do it, you can wiggle your way through all the problems, but it's not the portability high-level thing that HDF5 is trying to help you with, right? You should be able to get very close to optimal bandwidth on the machine from an I/O perspective. With HDF5 or NetCDF, we rely on MPI to do the right thing, and it almost always does. So you shouldn't feel like you have to revert off to some lower-level thing. If that's the case, you should come talk to us, somebody. Right, one of the I/O middleware guys. So I'll try to cover, we'll see how I do in time. Comparisons, parallel and serial. What does that look like in terms of, there's a lot of layers here. How do we do composites and other things? We've talked about this a little bit. And particularly collective and independent I/O and some of the restrictions or benefits of data set and metadata I/O. So I try to stay away from some of these things, but I'll be here all night, late into the evening. If you've got a quirky thing that you feel like, oh, well, this probably only applies to me, first off, ask the question. It's great. It's nice to hear those kind of ideas, and maybe somebody else has the same problem, and I could cover you all. Or we'll talk later tonight. But still, happy to talk about some of these more oddball scenarios that you run into. Virtual data sets in parallel is mostly what I meant there. But. All right, so big picture, parallel HDF5, sometimes PHDF5, just to make it shorter. We do everything through MPI/IO. If it's parallel HDF5, what we mean is we're doing I/O through MPI, not the more modern threaded parallel programming, that side of things. No, this is MPI parallel jobs. It should be portable to different platforms programmatically. The files are identical to the ones that you would otherwise create from a serial program, so you don't have to worry about that. You can create things on your laptop and move them over to a supercomputer or the other way around, doesn't matter. It's all just fine. Basically, we augment the standard HDF5 API with some calls and some semantics, or etiquette, sometimes we say. So it'll have that same exact framework we looked at earlier, these 7 basic calls with a couple of property lists stuffed in there to say, hey, I'd like parallel I/O right now. So we'll build up off of this. There's a lot of layers involved, though, right? So we have to kind of talk and give hints to the different places along the way. So your application's dealing up here, stride is a bad word, spread across many ranks in the HPC system. All of them make calls into HDF5. Like I said, we rely entirely on MPI to do the right thing, and it's always good, except when I bug Rob, and he says, oh, you broke it again. And then we fix it. There's still usually a single shared file that gets created at the bottom of this, although on a big parallel file system, that's going to get spread out across a lot of disks at the bottom. So here is a very simple real code instantiation of that framework I gave you earlier. So you don't see it getting used in any meaningful way here, but this is a file access property list. Sometimes we call them FAPLs, okay? So if I slip and I say FAPL later on, it's a file access property list. So you're gonna go create your file, you give it whatever file name you want. Here's that place where you gotta go describe your array to me, and I'm gonna go create a data set, and it has a native integer type, and that's data space that we created earlier. And then we go off and we write an array down into this file. And it uses dataset transfer property list, DXPL, which I'll show you in the next slide. But again, we're doing a native to native int directly into a native int in the file. So if you're on the little Indian machine, you're gonna make a little Indian data in the file. Big Indian machine, big Indian data, right? No more VMS. No mixed Indian stuff. We support it, but you cannot get one now, except Glenn, who has one. All right, so if you wanted to do a parallel version of this, right? Somewhere in your code, you initialize MPI init. You only have to add in, hey, by the way, I'd like to actually use the MPI-IO file driver for my file access property list. And you have to, same as before, you have to give it your MPI communicator and the info objects. And then you go create the file. It's fine. You're going to do it on all the ranks this time, though, right? Because it's a parallel program. All the ranks create that array or array description. They all collectively make the same call into HDF5 to go create a new data set. And then you want to write your array from all those different ranks into this single data set. I'll show you about subsetting later, so it's not on this slide, but most likely each process in your MPI job is going to have a part of the array, and they're going to write out a buffer that gets put in the right location by MPI's collective I/O in the files data set. But that's what we're saying here, is we're creating a dataset transfer property list, and we're saying, hey, when I use this dataset transfer property list, do collective I/O with MPI. And then we go ahead and use that dataset transfer property list for our dataset write. And then eventually, you shut things down, close the dataset, close the file, and MPI finalize. So initially, moderately simple. Any questions about it? Like, I've gotten bit by this, I like this, I don't like this. I'll show you how to optimize stuff more. But.
I'll just point out, it's not a question, but the line about turning on collective I/O, that for a decade was my secret trick on Blue Gene to make people go fast. And so now that you know this, my problems are now easier to solve, more interesting to solve, I guess. But this is a good one slide to remember. Because of the way HDF5 is designed, that's how you get to go fast on certain machines. And if you don't do that, you won't go fast. So.
Probably not, yeah, right. And I'll add on to that, exactly. MPI-IO says blah, 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 write at all, right? It spells that out for you in the API call that you make. It says at all, right? That's a collective call. And in HDF5, we default to independent. So, as Rob says, If you don't put these 2 red lines in here, you default to independent, and we will not know that everybody is here to do this I/O. We will not be able to do collective I/O for you. So HDF5 relies on some extra, outside the band kind of information to pass in to your write call instead of renaming the write call to be a collective write call. People go off and write little wrappers around HDF5, H5D write that are like, I want this one to be my collective one inside my app, and that's fine. But generically speaking, if you're programming to the API directly, you have to set this up and then pass it in, because there could be other options that you want to pass into your dataset write call besides do this collectively. And so we allow some flexibility there. But yes, exactly. So etiquette, right? How do I use this effectively and not have my program hang? Parallel HDF5, it opens this shared file with the MPI communicator. It gives you back a file ID. It looks like, to your application program, looks like just every other file ID that you get. But you got to access the file with that one. If you reopen it later with a serial thing, you'll confuse everybody. Just stay with one file ID. You can open multiple files and use different communicators to go access them. That's just fine. We don't care. In the JIT, if it's a collective API call of whatever sort, everybody's got to go do it. If for whatever piece of logic in your application code, you get everybody but one, you will hang. Your app will just stop, right? Because somewhere in there we've got some communication probably that we're going to need to hear from process 72, and 72 isn't here, and he's never coming. So we're going to sit there forever waiting for that guy, right? So collective means collective, everybody. And for historical reasons, anytime you modify the namespace or kind of structure of the HDF5 file, if you want to create a new data set or add an attribute, extend the dimensions on a data set, all of those operations currently have to be collective. So these kinds of things. And I would encourage you to kind of go look at the URL and say, hey, all right, if I use one of these API calls here, I will make certain that my app calls it collectively on all the ranks. Now, I'll put in a little caveat here that we've got funding for our ECP project for HDF5 to allow independent metadata operations, and I would expect you to be able to do those kinds of things by the end of the year. We've got the design all done, we've got all the infrastructure built, we're just kind of putting our Lego pieces together, and I expect in a month or two we'll have prototypes running for independent metadata stuff. But right now, and I will tell you this, HDF5 does, I'm sorry, go ahead.
This is slightly off topic, but so for the HDF5 object identifiers, in C they're all the same type, and so type checking gets delayed to runtime.
Yeah.
Is there a reason for that?
Lots and lots of battle scars. They're kind of equivalent to void pointers, right? Because when we were doing earlier with HDF4 and the versions of software before HDF5, naively, we put the struct definitions into the header files. And then we return pointers to the struct things, right? Whatever the data set equivalent is in HDF4 or the file equivalent was, fine. But then people play with your header file and they go, hey, you deleted field X from the header file and I read X out of your struct directly from your pointer. Put it back. It's no, it's better now. You need the new way. And they're like, no, I do not care. I have certified this for the XYZ thing, piece of hardware. You must put the X field back into your struct or whatever, right? So we learned, and we give back very generic things now that they have downsides, but they have upsides too. So that's why. Probably in any programming environment, when you get a very generic looking thing, it's a programmer with a lesson learned. Sorry.
Yeah, I was wondering, I followed that link, and actually the HD write doesn't come up as a collective call.
Right, it's not required to be collective because it defaults to independent. You have to opt in, like I was saying here, to make it collective. These other calls on that link must be collective. There is no independent.
When you said the MPIO collective attribute, or whatever you call it,
Yeah, property.
the property list, then it has to be collective.
Yeah, once you've done that on that property, anytime you use that property list, that goes, the collectivity goes with that property list, wherever you use that.
And if not, even if I open the file collectively, then everyone can do write independently.
Yes, exactly, right.
Is it possible to mix?
Sure. Yeah.
So sometimes do collective calls, sometimes.
Yeah, except the metadata. The metadata with these calls, right, those ones have to always be collective. But raw data elements to data sets, you can do independent sometimes and collective other times.
But I mean in the same running.
Sure. Yeah. Sure. Yeah. I was going to mention here for the metadata one, I'm sorry, was there any other questions? No? Okay. For the metadata ones, I'll tell you why, and this is annoying, and you'll probably find it sometime. I said, well, you know, process 72 isn't here yet, right? For the metadata, for raw data, you'll hang here. It'll be really obvious. You know, the dataset write will not return because we're waiting somewhere in the middle of the dataset write for some process to come in and it's not getting there. But for metadata operations, we do a lot of caching to improve performance in HDF5. And so we'll cache your changes to the structure of the namespace in the file. And we'll go, it's okay, man. And we'll cache that change, the write, to the metadata in the metadata cache in HDF5, and say, sure, fine, your group got created because that's what it looked like to us. But if everybody except process 72 did that, then everybody except process 72 has dirty metadata in their cache and process 72 doesn't. So later on, 55 calls later, right, really painful for debugging, 55 calls later, when we try to evict the dirty metadata that got dirtied with whatever that call was that process 72 didn't participate in, we're all waiting around for process 72 now, and he ain't coming. And so your program will hang like way later, maybe even at file close, right? So if you get into these funny operations like, I think I did everything right, probably you missed a metadata call on some process rank somewhere because of whatever application logic you had where that guy didn't participate in creating that group and you thought it would be okay, and it's not. And like I say, if you get down to the file close and it hangs, you got to backtrace up a little bit from there. Rob was mentioning earlier, I think somebody asked a question about flushing. And you can use the H5F file, flush operator, as a debugger in those kind of hang cases. If you get down and the file close is hanging, you can kind of bisect your way up, right? You can put a flush a long way up in your program and say, well, it's still okay up there. So you know that somewhere somebody didn't participate in the metadata operation between the flush and the close, right? And so you bisect down a little bit more and try flushing again, because flush is collective, and say, oh, everybody hung on that flush. Well, you know, you bisect your way up to the point where you go, oh, I forgot to create this attribute with rank 72. So those are two really good debugging things. I don't have them here in the slide, but you'll see it. Straight out tutorial examples. There's a lot up here. Many, many things and more web pages to go. Sorry.
Just a question about H5 Flush. Is this journaling in there? Because quite often it's the case that I don't crash in writing and then my files go out.
Yes, it does not do that. HDF5 does all this caching, right? And if you crash somewhere along the way, it's very likely that, well, some or all of the metadata changes haven't made it out. And the really bad case is if some have made it out, because we've changed half the B-tree nodes that needed to get modified in order to update your group index or whatever, right? And then when you try to open that group, it goes barfs at you. So flushing will help with that, but you have the performance problem of, well, you just wrote out the data from the cache. Now, to go back from that a little bit, we do have performance mods that are coming along that do incremental updates in a safe manner. If you're interested in that, let's talk afterwards, I think, because it's not ported to parallel and there's some caveats about it, but it's a direction we're trying to finish up exploring for part of the ECP work we're doing. But yes, it is kind of a valid problem that if your app parallel or serial crashes in the middle of updating changes to an HDF5 file, you could end up with cached data that didn't get written out. And you can flush to go fix some of those things. You should fix your app crash. But I know every time, sometimes your timer runs out on your allocation to get it, so fine. All right, so, sorry, let me go back here. Tutorial examples, lots and lots of them examples to do all kinds of various things. I'll cover a few more of them in the talk, but there's no possible way I can cover all this in one talk, right? So, Rob mentioned this earlier, right? Lustre files get striped over multiple disks. There's actually rating and all kinds of fun things happening underneath the covers. And your HDF5 file participates in that and gets divided up. And these little blobs in here that you can't read very well, sorry. That one was supposed to say object header, and that one over there says very, very dimly dataset data. Get sliced by the striding across the OSTs in the parallel file system. And we'll talk a little bit more about that too. So back up a little bit towards the file format, right? Because this matters about parallel I/O. The description of the metadata for your data set is what we call it here an object header, right? And the data type and the data space are the big things. There's some more junk in there. Any attributes that you write for that data set, they'll get put in the header. And all that gets put into this cache I mentioned earlier for performance reasons. And then your data set data is probably off in a disjoint section of the file. Very kind of straightforward in a sense. If you use chunking, as I was saying earlier, to allow you to be extending or subsetting or compressing, all that happens. Plus, we need a chunk index to look up where those chunks landed in the file, because as you can see, they're not always in linear order, and they're not always packed one next to the other. So we'll need to look those up over time, especially they might change. And so again, this is getting put into your file. HDF5 does all this for you. You never need to see all this stuff. But when you layer that on top of a parallel file system, it's like fun, which is part of the reason why we rely on MPI to do the right thing, right? If we describe all the elements that we're going to go do I/O on in your chunk data set to MPI, and we say, hey, all the ranks are going to do I/O on here, and rank 0 has all the data for this guy, and rank 1 and 2 and 3, then we allow MPI to get the full set of information. It knows about the file system. It knows about the striping, probably. And it can do some optimization about getting your data out to disk in a nice, efficient way, and you don't have to think about it. So you get all the benefits of extensibility and compressing your data, portability, and we use the layers of the I/O stack in the best way possible. Your app doesn't have to think about those kind of problems. So just kind of a caveat about magic that's happening underneath you. So talk a little bit about collective and independent. Rob hit this really well earlier. So generally speaking, what collective I/O is trying to do for you, it's combining multiple smaller I/O operations into bigger ones, right? This is how you improve performance for every single thing you do in I/O, right? Well, make a bigger buffer, right? Hand it on down the next layer. It's not necessarily always better to do independent or collective. There's good reasons to do one and the other. Collective at least gives you the opportunity to give it to MPI and say, hey, now you know the whole picture. Could you possibly do something to make this go better? And it may very well turn out that it can't. But at least it could try. Whereas if you just divide it up into a bunch of independent I/O operations, it has no clue. It just has to do each I/O operation independently of the other guys, and it doesn't know what the big picture is. So collective is nice from that. It may not get you better performance, but it probably will. And again, this is very basic MPI stuff, but if your first process is calling whatever collective operation A then B, you gotta do that everywhere, because if you flip it, you get a deadlock, right? Your MPI app will well, not crash, it will hang, which is more annoying. And I don't want to leave you with the impression that collective always means there's communication, or even that they synchronize at that point. It could just be that everybody has to maintain the same state as you go through all those ops. And later on, they're going to rely on that state to do something else fancy in another collective operation. So you might have a whole series of collective ops that do no communication and do nothing except update state locally, and then later on, they do some communication or some other operation that relies on their state being identical, and that's why the earlier ones had to be collective. It's true about MPI as well, too. Any questions here? This is a good, sometimes collective and independent I/O. We've hit a few already, which is great. No? Okay, well, something comes up. All right, so performance tuning a little bit more, right? Because I'd like it to go fast. This is a summary statement. Again, same thing here, stuff I've covered. How do we improve our performance for raw data I/O? Do less I/O, right? Well, yeah. You know, maybe chunk layout would work for you. Maybe it would work in a better way, a different kind of chunking layout. If you're writing to columns, don't make your chunks horizontal. You know, things like that. Maybe you need to aggregate or balance your I/O in some way. Maybe there's some alignment going on, although we're hoping we can push that down to MPI and we don't have to deal with it, right? Generally speaking, the latest version of the library's got the best optimizations for everything. Maybe you want less attributes sometimes in your metadata. Like you're gonna create one attribute that has a compound type that has several fields in it. Instead of writing out 5 different attributes, you write out one attribute that has 5 fields in a compound type. That might be a twist on your data model that you're storing in HDF5. Come talk to me if you think you want to play with the caching algorithm. There's literally like 50 knobs, and you can get lost pretty easily in there. But the default is good, generally speaking. And as we said earlier, there's a lot of layers to go optimize. There's knobs to turn at each layer if you'd like. We try to hit all these things generally speaking, but the abstractions leak through sometimes. And so for whatever reason, if your luster stripe factor is really, really crummy on this machine, you may have to tweak that yourself because HDF5 has no idea exactly what you're trying to do at your app code level. And it's the same all the way up, right? Hopefully there's not worse and worse numbers of knobs, but it's mostly constant these days. People are, you know, each layer is trying to do a better job of automatically helping you out. We get it right most of the time. So, if you have performance problems, here's some tactics to go and try. So, textbook problem, I mean, it's kind of old in the sense that it's not very big, but the problem is, you know, identical on today's bigger systems. So the user had a very, very tall, thin array. You know, it was probably X, Y, Z temp kind of thing going on. And they just were outputting a mesh and temperature for each grid location, right? 230,000 mesh nodes, maybe, mesh points. But they're doing it with independent I/O, and they're going like, why is this crazy? What did we do wrong, right? HDF5 is broken. It's like, no, it's not. You probably just shoved the square peg in the round hole. So they, you know, again, background here, they were doing, say, 4 processes, writing out floats or doubles. Well, sorry, doubles here. And if you run this with 4 processes and 1,000 things, this is pretty slow, right? 1,000 elements to take about 2 seconds. And when you doubled it, you know, it got twice as slow. It's like kind of weird. Why is this happening? Why, I thought collective I/O was going to fix my problem. So, terrible. If you want to do some debugging yourself and you want to build a version of HDF5, these are the 2 parameters that you want to give to the configure line for parallel HDF5 to do some debugging. Turn on the debugging inside the library at the configure time and make certain you build with, you know, a parallel build of HDF5. Then you can set some environment variables that give you line-by-line output. So don't do this on really big files. This is while you're debugging. You'll get some output that looks a little bit like this. These first ones are a little anomalous, and you think, oh, that's kind of odd. Where'd 96 come from? Just ignore those. These 8-byte ones are your problem. All these offsets, just incrementally here. You notice all these guys are at offset 0, so this was a chunk of metadata at the very beginning of the file. And we fixed the replication there too, so don't worry about that part. But anyway, why are we writing out 8 bytes at a time, 4,000 of these things? That's craziness. So everybody was writing out an independent I/O, and they would write one element, and then they would skip down to the next byte, and they would write array elements offset by 32 bytes at a time down the I/O pattern. So you say, I know about chunking. So I will, since I'm writing out a column, I will make my data set be chunked by a column, and therefore that metadata, just don't worry about it, and then the I/O goes out as one chunk at a time. My process has one chunk in the file. I'm writing out a column. My chunks are aligned to a column, and I go, boom, I hit the, go fast button, because this is 100 times faster, right? Still small files, I get it, but you can clearly see that you've optimized things quite a bit by aligning your HDF5 storage with your I/O pattern. So a lot of the thinking about how do I make this go faster is your I/O pattern reflected well in how HDF5 is trying to store your data? Now you can also get basically that same benefit if you do collective I/O, because you'd give the whole description of that column to MPI, and MPI would go, oh, hey, you are writing these bytes, and he's writing the bytes right next to them, and then the bytes next to that from the other rank and the other rank, and it collects them all into one big I/O description, sends them over to one rank, and does the I/O. So collective or chunked, depending on your scenario. Obviously, chunking will work in a serial program, and collective is only going to help you in a parallel one. But collective and chunk is just fine, too. You can do that. So, I mean, some ways it's a silly graph, right? But, I mean, clearly you solve the problem of, gosh, it got really bad, and I fixed it. All right. So any questions? Next, I've given a couple of slides, again, at the URL at the bottom, slides, examples at the URL there. If you'd like to try looking at those things, the first one is an independent I/O and a contiguous data set, then collective, then independent to chunk data sets, and kind of drawing from those two, a little bit of hands-on for yourself, go make the chunk data set be collective, right? It's a pretty straightforward mod, given the things I've told you and the examples to draw from here. You can do that. And again, for the examples, this first one is creating groups independently. You'll see that there's different group names on every rank. We sprintf the rank into the group name, right? So every rank in your MPI job will have a different group name as part of the process. And eventually it'll hang, either at the file close or earlier, depending on how many HDF5 calls you have. And you can take a look at what the difference of those two things looks like. Just sort of go play with this on your own side of things. So back into, okay, I'd like to optimize this. There's two kinds of tools that we have for doing I/O benchmarks, right? There's kind of the what is the system capable of tool, a benchmark, and then a profiler of like, what is my application doing right now, right? And the first one is kind of really interesting to say, oh, I'm running on Cori, I should expect that the performance to the Scratch file system peaks out at 400 to 500 gigabytes a second, right? Fine. I'm getting 300 gig a second, probably fine. Not gonna optimize too much from there. You could play with it and get some better performance, but you're probably in a really good zone. If you're down in the megabytes per second, you have a problem somewhere, right? So that's nice to kind of get a sense of that. And then once you say, oh, I got a problem, then you can look at the I/O profiling tools. And Phil's already talked a lot about Darshan. It's a great tool. You should go use it. H5perf is a little bit more in the benchmarking side of things. I'll talk more about that. And, there's trade-offs between them. H5perf has a number of different patterns that you can work on to kind of reflect what your application I/O behavior is. For whatever reason, your arrays in memory are stored one way or the other, and you need them in the file in a different way. Very contiguous stuff, scattered, I would call it, gathered in a sense, and then just both discontiguous. So this H5perf tool, there's a serial version if you'd like to just kind of run it on your laptop or on another machine to check out various serial performance aspects of things. You can, if you're running the parallel version, see what the actual POSIX performance is if you didn't do collective I/O. You can see what MPI would do if it was doing collective or not collective, if you'd like, I/O on that system. Kind of the baselines, right, that you can work from for a high-level library. They're not going to exceed these numbers, probably. We do caching. In certain weird circumstances, we've had to go faster, but that's very strange. And then what, well, if I did the right thing with HDF5 here, what sort of performance should I get out of this file system? Yeah, and again, you're managing your expectations mostly. Serial run on one of the systems, NCSA's Blue Water system. You can see that HDF5 and the averages here in the middle of the red bars, they're a little down for HDF5, but they're in the ballpark. And you probably would not be too excited about differences like this. It's a little weird that this is so much less in this case. But maybe that was just a bad run. Over here in the maximum performance, we're probably in the right zone. Serial, I'm sorry, that was serial, this is parallel. So MPI/I/O is mixed into this guy, right? And you can see that HDF5 is really moderately closely tracking with a little performance penalty, the MPI performance. So that's what you want, right? Our goal when we do parallel HDF5 is let's come 90% of MPI/I/O. We do a little bit of extra metadata. You're not just writing on an array from all your ranks. There's going to be some extra overhead, but it's close enough that you probably get all the benefits and you don't lose too much performance. I won't talk about this. We hit this earlier. Let's see, kind of examples. Should we hit? We got about 15 minutes, right? Any of these, like, jog somebody's memory? I have this problem, I've had a question, anything else that somebody had been thinking about at this point? I can give some application examples. I might touch one of those and then talk a little bit about future directions with HDF5. I've got a few examples for different apps in the slides if you download them. Okay. All right, so this is kind of a classic one that we pointed at a few years ago, but run on LBL's Hopper machine, which is 2 generations back, but still. Well, let's pause here, right? So we're dealing with some application that was doing HDF5, and when it all diced down to the end, we're doing this into a single shared file from many, 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 many layers of the up from the storage system. We have these enormous output files. We used H5part, which is a high-level wrapper on HDF5. It's now called H5hut, HDF utility toolkit, I think. Hut always seemed like an odd one to me, but okay. I didn't write it. So it writes out these 8 arrays from this VPIC application. Basically turns out that you can basically max out the I/O performance from the system, single shared file. MPI did its job, HDF5 did its job. It's a fairly straightforward set of arrays that you're writing out. It's not a complicated HDF5 file. But if you've got a good application that's doing reasonable I/O, you can max out your performance in the single shared file and not have to worry about it too much. There's going to be corner cases. more details here, I won't worry about. Occasionally we run into this problem. We're trying to get the release for this guy out here, but it's sometimes tricky. When you shut down an HDF5 file, we made the mistake, when you close an HDF5 file, we made the mistake 20 years ago of saving 8 bytes. We saved 8 bytes by not storing exactly how long the file was to detect that the file had been truncated, just part of the safety factors in the file. Like, has this file been truncated or not? You should store the file length inside the file. We didn't store it in there. We instead truncated the file to whatever size it was supposed to be and then stored a derived value from that in the HDF5 metadata for the file. So we have to, the current library will truncate the file to the right length. And truncating files in MPI has historically been an enormously painful operation sometimes. If you default to the original configuration and then you turn off the truncation, you get 3x better file closes. This was annoying. So we're trying to fix the file format to incorporate the 8 bytes that penalizes us so badly here, right? It should come out soon, I would hope. I think I said this last year, though, so, but, you know. It's a file format mod, and sometimes the file format modifications, because of all the backward compatibility baggage that we want to do the right thing on, that restricts us from updating the file format mod. But I just explained all this. You can look in there for more details. Another place where, actually, you know, Rob mentioned this earlier, well, what if I want to do I/O to multiple data sets in the same file? Well, that would be awesome, and we would be able to give a bigger picture even to MPI, and PNetCDF has some special things where it allows you to aggregate up these I/Os, and then later on just say, hey, remember all those I/Os I told you about? Go do that I/O, which gives an enormous performance boost in the right scenarios for user applications. And so we leveraged all the knowledge and experience the Argonne guys had done, and we said, oh, this is a good idea, we should do this. So we've also got prototypes of a multi-data set collective I/O operation that you can experiment with until it gets into a release. It's annoyingly complicated, and we break MPI. This was another place where we broke MPI's data type description, but it's okay. Obviously, it's one of those, gosh, it was terrible, and boom, it does the right thing, right? So if you translate that multiple data set write calls into a single data set multi-write call, that's a huge win. Again, just one of those, oh, yeah, we should do that. Let's see. About 10 minutes. I kind of like to hit future directions and take more questions. So I'm going to skip past these guys down into the future directions. They're there if you'd like to look at them in the slide deck. I will mention this, though, if you care about writing a lot of metadata into HDF5, there's a couple of knobs to turn on to go say, by the way, I will make certain that I do all my read metadata operations, my metadata read operations like group opens and group dataset opens collectively, and then we can speed those up because everybody will be there. Come talk to me later. It might be a useful thing to go talk about a little bit more. So roadmap questions and general questions. We have a feature that we're working on. We have a good prototype working in serial for doing what we call single writer, multi-reader. Right now I said earlier, oh, you can only have a single writer into an HDF5 file. And because of the caching, currently, without this feature, you can't do reads against that because the writer guy, he's probably got some stuff cached up, and then the reads will look wrong to the readers. So we've made some changes to how HDF5 works, and this single writer, multiple reader, or swimmer call or feature will allow a writing application on a camera system or something else like that, and maybe a light source to be writing into the file and readers to come in and get the data out of those files. Can be very, very, very useful. We've got a good prototype for doing async I/O in HDF5, which means we can completely overlap your I/O with your compute and hide it. which makes it look like your I/O time goes to 0, which is wonderful. Should have that also in the fall. We've got good prototypes. If you really want to experiment, you can come talk to me later and I can point you at the prototype and you can look at it. I don't think we're going to get to internal threading this year, but it would be really nice if we could do something like that. Virtual data sets are done. This virtual object layer, it's a way of allowing HDF5 to read other file formats or object storage systems or anything else that you'd like to go put underneath the bottom. So you're not dealing with the traditional HDF5 file format necessarily. You can read a NetCDF file directly or an Adios file. We've got drivers, plugins for those virtual object layer connectors available now if you'd like. There's no capability in HDF5 to do queries like, hey, tell me the region where everything is above 72 in my data set. But again, a prototype with ECP funding should be coming along with that this year. We've got a prototype for client server, but I'm not super excited about it. There's a better one for cloud. If you are dealing with an S3 compatible cloud storage model like Amazon's, we can set up a cloud server and then your HDF5 accesses into the S3 compatible cloud can happen transparently to you. Not an HPC scenario most of the time, but NASA likes it for a lot of different things. Fix some of the scalable chunk index problems we've had, metadata aggregation still working. That's an ongoing problem. We fixed a lot of things and there's still things you uncover too. We've got some funding from Slack to go improve variable length sequences in HDF5. So that's probably going to be about a year from now, I would expect. Fault tolerance with the crashing is very annoying. Swimmer actually fixes that, which is what I was alluding to earlier. If you turn on Swimmer, then the safety factor, because of the way the readers would have to come in and get a consistent view anyway, it means we could crash at any point in time and have a consistent, maybe it didn't get all the updates, but it's consistent and correct. It just might be delayed if you crash. So that's a useful aspect to tying the Swimmer piece into fault tolerance. And there's always performance improvements and other things going on. That's probably where I can wind up. Any questions, comments, anything else? We can talk more about I think I hit most of these, really. We're funded through a number of different DOE and other places to keep adding more features in HDF5 to sustain this for the next at least 5 years. We've been around for about 20, so expect to be around indefinitely, I hope. Yes?
A question about building. I saw that you have like H5CC, essentially compiler wrappers.
Yeah.
So is there, two questions. First, is there like CMake support? Do you have like a CMake config that you can? Yeah,
you can build the entire HDF5 package with CMake.
And you export the config so you can load it from another?
I think so. I'm not a real strong CMake guru, but I believe CMake is very well supported by now.
All right, well, and then I guess in terms of the compiler wrappers, is there like a specific order? So sometimes ordering matters on those things, like in terms of MPI versus?
Yeah, if you configured HDF5 with a parallel and you're using MPI, we will wrap the MPI compiler wrapper with the HDF5 one and then nest them on down. Yeah, HDF5, well, it's higher up in the I/O stack, so you should probably expect it to be the top thing you invoke, generally speaking. Lots of people have, build scripts for their apps. They don't want to mess around with us, so it's a convenience thing mostly.
Yeah, what's the status of compression with parallel files?
Compression in parallel files is now fully supported. You can, as long as you do collective I/O, we have everybody here, and we can decide about how big those chunks of compressed data will be and distribute that so everybody doesn't get confused about how big that ended up. So yes, collective I/O and compressed data sets works well now.
Okay, so it's in production now?
Yes, yes, I believe so. Yeah. Yes, sir?
So my question is about variable length record.
Mm-hmm.
So in the beginning it looked like we can nest the types and variable lengths are supported, but in the end you want to as part of improving, you want to improve the performance of variable length records, or what's the like?
Yeah, so variable length, performance, and nesting. So the answer is yes to both. You can do it, and right now the performance is bad. Because when we store things basically as an array inside HDF5, which does not jive very well with variable-sized things, right? So in order to get to the variable-sized thing, we have to store a heap ID and a way to get to your variable length thing somewhere that can store variable length stuff. So every variable length element in your data set is going to require an extra lookover to go get the variable size. Now we take the heap blocks and we cache those and we aggregate them so that it's not at 1-to-1 I/O per variable length element, right? But it's an extra overhead in those kind of things. And if you nest them, well, now the first variable length lookup gets a thing with more heap IDs in it, and it goes over there to get each element's first, you can see that the performance would not be good. So yeah, we've got some funding from Slack I think what we're going to do is probably make fold nested variable length stuff into single blobs so that you don't have this separate look aside, for each level of nesting that you do, and then change the format. Instead of going into another heap with kind of this other bad behavior, we're going to have co-dataset storage, one with the arrays and one with the variable length stuff, all so we can stream them nicely in. So those are my two kind of solutions for the performance problem. So, yeah. Sorry?
Why was HDF5 implemented in C rather than C++?
C++ was non-standard in 1998. And it was not completely convincing that it was going to exist on supercomputers, much to our chagrin today. But yes, C was it, man. Although Microsoft needs to upgrade the standard in their compiler, because for whatever reason, they just don't. And so there's certain standard parts of C99 that they still do not implement. We have custom workarounds for building on Microsoft platforms. It's very nice. Anyway. Sorry.
Does the wrapper for C++ take advantage of any C++ features of type inference?
The one that we ship is very naive. There is another one like H5 CPP or something like that. Stephen Varga, I believe, is the author of it, and he wrote it himself, and it is magical in all the normal C++ ways. So try that one. Ours is very boring. Very, very, very boring. But the other one is very magical. Anything else? Sorry? No? Okay. I think that's it then. I got 50 seconds left, so you guys have been very good. You filled all the gaps and got me to the right place at the right time. Thank you for your help, your participation. I'll be here until later in the evening if you want to talk about specifics.